Hi everyone, I'm Yong Song, a second-year PhD student from MIT AACL. Today I'm going to talk about some recent advances in contrastive learning for pre-trained language models. Contrastive learning has been widely applied in self-supervised learning for many domains, including computer vision and speech processing. The model pre-trained using contrastive learning has achieved state-of-the-art results in these domains. However, in NLP, contrastive learning is a recently emerging direction. So we will first start with why we need contrastive learning for NLP and why it is more difficult to apply contrastive learning for NLP tasks. So let's first talk about why we need contrastive learning and how to do contrastive learning. So we need contrastive learning because we want to obtain a good representation space such that similar inputs can have similar representations in the embedding space. For example, if you have two images from dogs, their representations should be similar in the vector space. And if you have two different augmentations from the same image, they are referring to the same object, so their representation should also be similar. So this kind of similar data pairs, we call them positive pairs. And on the other hand, if you have two images that from two different objects or from two different classes, their representation should be dissimilar from each other. And this kind of data pair, we call them negative pairs. So how can we train a model to maintain this kind of property in the embedding space? We have a lot of different contrastive learning framework can achieve this kind of effect. And there is a very famous framework called SimCSE. And the idea is very simple. It just do two different augmentations from the same image, and then the training objective will make these two representations from these two augmentations be close to each other as much as possible. And for any other random sampled negative pairs, they just make the representation be dissimilar to each other. And this kind of contrastive learning framework has been achieved successful results on the computer vision downstream tasks. However, in NLP, contrastive learning is not very popular as we have here in computer vision. And one possible reason is that actually people has been using some ideas similar to contrastive learning for NLP, but we don't call them contrastive learning. For example, if you look at the training objective of Bert, the mask language modeling task, you can see we have a sentence here, how's the weather today? And we mask one token in the sentence and replace it with a mask token. And in the output layer of Bert, we try to predict which token has been replaced, what's the original token. So here, our input instance will be the contextualized representation of mask token. And we want to match this representation to the non-contextualized representation of the correct answer weather. So we can see these two representations as kind of positive pairs. And for negative pairs, because for our prediction test, we need to make the representation, the contextual representation of mask to be dissimilar to all the non-contextual representation of all the other words in the vocabulary. So actually, we also have negative pairs. So basically, training the NLM model is kind of similar to training a contrastive learning task. But there's a difference because we have finite vocabulary size for Bert. It's around 30,000 of vocabularies. So this finite vocabulary set prevents us to do any negative sampling process. We can use all the possible examples, all the possible words in the vocabulary as your negative pair. So we can just train MLN as a simple token level classification task without using negative sampling. However, there is also some other task that has infinite possible inputs. For example, if you are dealing with sentence level task, we have infinite combination of words, so we have infinite possible sentences in the world. So it's not possible to use all the sentences in the world to train your model. So we need the negative sampling process. So the sentence level task will be a good field to apply contrastive learning to learn a good representation space. So in the following of this tutorial, I will mainly talk about the sentence level representation. So I will first introduce why we need sentence level representation and what's the model before Bert came out and what's the model after Bert came out for sentence level representations. And most of this model after Bert is about doing contrastive learning based on Bert. So for the sentence level representation, why we need this kind of model is because we want to use this kind of sentence encoder as a backbone that can be used for a lot of different downstream NLP tasks. And the benefit of using this kind of sentence encoder is that we can fix this sentence encoder and only use it as a feature extractor. So we don't need to fine-tune this model for any downstream tasks. And we only need to train a linear layer and to do a simple classification, and we can achieve good performance even without a lot of label data. And also, if we have a sentence encoder model, we can extract the sentence embedding for all the sentences in the corpus so that we can do clustering or semantic search very easily just by inner product, because we can measure the similarity of all the possible sentence pair very easily. And also, if you have an unsupervised method that can train a sentence encoder, that will be very desirable because we can apply to all the languages, not only in English. So we can train a good sentence encoder even without any parallel data. So in the following of this tutorial, I will mainly focus on supervised method instead of supervised methods. So let's go back to the time that Bert hadn't came out. So before Bert came out, there's already some papers working on sentence embeddings. So for example, in the skip solve vectors in 2016, they tried to train a sequence-to-sequence model and to encode the previous sentence and then try to decode the next sentence. So the vector between the encoder and decoder can be seen as kind of sentence embedding for the previous sentence. So that we can use that vector as a good sentence embedding. So after this paper, there is another paper called Quick Solve Vectors in 2018. They also doing some kind of next sentence prediction, but the difference is that they don't need the decoder. They can just use a classifier to try to classify which sentence is the correct next sentence. So these two models, even without the help of Bert, they can somehow achieve a good performance for sentence embeddings. But in 2018, Bert came out and it changed the whole NLP community, and all the people started using Bert as their backbone for any NLP downstream task, including sentence embeddings. So people start to try whether we can just directly obtain sentence level representation directly from Bert. And unfortunately, people found that if you just take the average of the Bert embeddings, or you take the Bert CLS vectors, you will obtain a very bad result. It's even worse than doing average growth embeddings. So Why is that happening? So it's because there is one problem in Bert's embedding space. It's called an isotropic problem. So it means that the representation space has some kind of degeneration, because all the embeddings in Bert representation space occupy a narrow cone in the vector space. So it largely limits the expressiveness of the vector space. So some papers start to try whether we can fix the Bert embedding by doing some transformation to the embedding space. So in this paper, Bert Flow, they try to do an invertible mapping from a Bert embedding space to a standard Gaussian latent space. So by doing so, they can improve the performance on the STS task. STS task here is a sentence textual similarity task. It's basically constructing by a lot of different sentence pairs, and we have human ratings for all these sentence pairs. And the metric we use here is the Spearman correlation between the model predicted scores and the human ratings. So you can see after applying Bert Flow, we can obtain a much better result compared to simply do average for Bert embeddings. So there is also another paper called Bert whitening. They do a more simple way to fix the Bert embeddings. So they use a simple whitening post-processing method, and their performance can be slightly better than Bert Flow. Okay, so after these two post-processing papers, people start to think about whether we can further fine-tune the Bert model and to extract the better sentence embeddings from Bert. So in the following, I will talk about a lot of different contrastive learning methods to extract good sentence embeddings from Bert. So if we want to train contrastive learning model for a natural language sentence, we have a problem here. We don't know how to do the augmentations for natural language sentence. For computer vision, we can just simply do random cropping, random flip, or grayscale to obtain high quality augmentations. But because of the discrete nature of natural language, it's not easy to do this kind of operations for a sentence. So in the following papers, they try to design some augmentations or some methods to construct the positive pairs. The first paper here is called Decoder. In this paper, they try to produce the positive pairs by random sample spans from the same documents. And the spans here need to be overlapping or adjacent to each other. And they also have different strategies to sample negative pairs. For example, they sample hard negatives from the same document, and they sample easy negatives from different documents. And by doing so, they can achieve a much better results compared to Bert Flow or Bert whitening. So it's a huge performance improvement using this contrastive learning method. And at the same time, there is another paper called Concert. In this paper, they try all the possible augmentation in the token embedding space. For example, they try adversarial attack, they try token shuffling, cutoffs, and dropout on the token embedding space. And they found that this method can also improve the performance of the STS task. And the performance is similar to the Decoder paper. And they also try to see which augmentation method works the best. So here you can see the shuffle and token cutoff are better augmentation compared to feature cutoff and dropout. And besides designing these positive pairs, we can also just try to generate the positive pairs from another language model. So in this paper, Dino, they try to generate the positive pairs by GPT-2XL. So they just have as input sentence and they try to generate two different continuation from GPT-2 and use these two different continuation to train your contrastive learning model. So here you can see the result of Dino is even better than decoder and concert, and also better than Bert flow. So it shows that it's possible to somehow generate positive pairs by another language model. And another method is about the bootstrapping method. So I think some of you may have heard of the BIOL paper. So BIOL tried to do contrastive learning without negative examples. So actually it's not contrastive learning. They just have positive examples. And they try to train this model by matching the representation from an online network to a target network. And the target network is actually the moving average of online network. So this can prevent the representation space from collapsing. And a paper also tried BIOL for sentence embedding. So here you can see the result is better than Bert flow and some other post-processing methods. However, it still falls behind the contrastive-based methods like decoder, concert, and Dino. So these results show that maybe contrastive learning with negative pairs is still a better way to learn representation for sentences. So the next paper is a very famous one. It's called SimCSE. And in this paper, they show that you can just simply do some dropout mask as your augmentation, and you can get a state-of-the-art performance. And the dropout mask augmentation here is not the same as the one that we used in concert, because in concert they are doing some masking in the when embedding vectors. But here the dropout mask is all the dropout layers in the transformer layers. So what they actually do is they have the same input sentence and they forward this sentence to the transformer twice. And because the transformer will sample different dropout mask for different forwards, so you don't actually need to modify the model architecture. You can just do two different forwards and you can get a good augmentation. And their result is even better than decoder, concert, and Dino. The performance has a big improvement. And actually, the author have tried all the other augmentation methods like random cropping, word deletion, word replacement, NLN replacement, but none of them is better than doing nothing, but just changing the dropout mask inside the transformer layer. So this experiment showed that changing dropout mask is a simple but super effective way to do the augmentations. And they also try different training tasks, like we do next sentence prediction in quicksort, and we can also try this for Bert, but it's not as effective as self-prediction. And they also try a dual encoder and compare it to a shared encoder. So the results show that one single encoder is a better sentence encoder. So here they also have some application study about the dropout mask. So they try to apply the same dropout for two positive inputs. By doing that, you obtain exactly the same representation for the positive pair. By doing so, the performance will drop significantly because your model is not going to learn anything by matching two already the same inputs. And they also try different dropout ratio here, and they found that the best dropout rate is around 0.1. In the SimCSE paper, they not only do the unsupervised setting, they also do a supervised setting. And the positive pairs are produced by the NLI, the Natural Language Inference dataset. So in this dataset, we have an entailment sentence and a contradiction sentence. So they use the entailment sentence as a positive pair and the contradiction sentence as the hard negative pair. So by doing that, they can get even better results compared to the unsupervised SimCSE. And the experiment also showed that if you use some other different supervised data to produce the positive pair, like doing back translation as a paraphrase, This kind of method is not as effective as using entailment data as positive pair and contradiction data as negative pair. And so if you compare unsupervised SimCSE with supervised SimCSE, you can see there's still a big gap between these two models. So it shows that there's still a large room for unsupervised models to improve. And the author of the SimCSE paper, they also try to evaluate the embedding space and see why SimCSE performs much better than other models. So here they use alignment and uniformity to measure the quality of the embedding space. Alignment means how close the two representations from the positive pairs are aligned together. And the uniformity means how well the representations are distributed in this vector space uniformly. So they try to plot the uniformity and alignment in this 2D plot. And the y-axis is alignment and the x-axis is uniformity. So you can see if you directly take the embeddings and take the average of the Bert embeddings, you get a very good alignment. But your uniformity will be very bad because of the anisotropic problem of Bert. And if you do some post-processing for Bert embeddings, you can get a much better uniformity because now your representation space is a Gaussian distribution. But your alignment will be compromised. So that's still not a very good representation space. So you can see SimCSE here, it not only achieved a good uniformity, but it also achieved a good alignment. So that may be a reason why SimCSE can outperform all the other methods. After SimCSE, people start to try to extend SimCSE to multilingual settings. So here, the paper SimCSE, they have a very surprising finding. They found that if you use a multilingual model like multilingual Bert or XLMR and fine-tune them with the SimCSE objective with only English data, the model can align all the languages together even without using any parallel data for other languages. So we can see in the figure here, the representation space for XLMR is not aligned at all. So all the languages are separated. But if you fine-tune this model with SimCSE objective, all the languages are aligned together. And this is without the supervision from parallel data. And here's the result for cross-lingual retrieval for the SimCSE model. So we can see the performance of SimCSE that are trained with only English NLI datasets. It's very close to the performance of a LabC model. The LabC model is a multilingual sentence encoder released by Google. This model is trained with a lot of translation pairs, so it's fully supervised. So the result here achieved by the SimCSE model is very surprising to me. Yeah, and I expect that there should be some different ways to improve this kind of unsupervised multilingual sentence encoder model. So after SimCSE was published, we learned that the augmentation for natural language is very hard because word deletion, synonym replacement, sentence cropping, and back translation, they are all outperformed by a simple dropout-based augmentation. So another question is, how can we utilize these augmentations even their quality are not so good? So here let's take a step back to think about why we need these augmentations. It's because we want to make the representations invariant to these kinds of augmentations. However, because the quality of this augmentation is not so good, so making the representations invariant to this augmentation will actually hurt the downstream performance. So does that mean these augmentations are not useful at all? I think no, because we can try to use these augmentations in a completely different way. we can try to make the representations be aware of, but not necessarily invariant to the augmentations. So let's look at some examples in computer vision to understand this idea. In computer vision, we have so many different augmentation methods like grayscale, 4-4 rotations, vertical flips. And you can see grayscale is a very good augmentation method. It can achieve a much better result compared to a baseline if you use grayscale to produce the positive pairs. However, 4-4 rotation is a really bad augmentation method because you can only obtain a much worse result compared to the baseline. So here we can try to do the things differently. We can try to, instead of using this augmentation as positive pairs, we can try to make the model be sensitive to these augmentations. So by doing so, you can see the performance of training the model to be sensitive to grayscale will be worse than the baseline. And if you train the model to be sensitive to 4-4 rotation, the performance is actually better than baseline. So here the results show that all the augmentation methods should be useful in some ways, but you need to choose the right way to utilize them. For grayscale, you should make the model insensitive to it. And for 4-4 rotation, you should make the model be sensitive to it. So how can we have these two properties in a single model? So we can have a multitask model here. So on the left-hand side is a regular Sinclair model that tries to make the representation invariant to the grayscale augmentation. And on the right-hand side is a prediction task. We try to predict the rotation angle of an input image so we can make the model be sensitive to 4-4 rotation augmentation. So how can we apply this concept to learn sentence embeddings? So here we propose a model called DivCSE. It's also a multitask model. And on the left-hand side, we have a regular SimCSE architecture that makes the representation be insensitive to dropout mask augmentation. And on the right-hand side, we have a generator and discriminator. The generator will replace some tokens in the sentence to produce augmentations. And the discriminator will try to predict whether one token has been replaced by the generator or not. And the model on the right-hand side is very similar to Electra model. It's also a generator and discriminator. But a huge difference here is that the discriminator is conditioning on the sentence embedding produced by the sentence encoder. And the gradient of the discriminator can be backpropagated into the sentence encoder. So the sentence encoder will try to compress the original information as much as possible to help the discriminator to distinguish the difference between the original input and the modified input. So here, our model is actually doing a kind of diff operation between two very similar inputs. So that's the reason why we call our model DivCSE. After training this model, we discard all the generator and discriminator and only use the sentence encoder for inference. So the result of DivCSE show that it's much better than SimCSE by 2% on the STS task. And also you can see what's the difference between SimCSE and DivCSE by looking at the retrieval results. So here we have a query sentence, this is not a problem. And the top one retrieval result from SimCSE will be, this is a big problem. So these two sentences has the opposite meaning, but their structure is very similar. So the SimCSE model was misled by the sentence structure. However, for DivCSE, the top one choice will be, I don't see why this could be a problem. So this sentence has a similar meaning to the query sentence, but their structure are very different. So this result shows that DivCSE will not be biased by the sentence structures, while the SimCSE are more easy to be biased by the sentence structure. Okay, so the next paper I'm gonna introduce is about using pumping to further improve the performance of SimCSE. So in this paper, Bert, they try to design or search good prompt templates to better extract the sentence embeddings from Bert model even without fine-tuning. So previously in SimCSE paper, they still use the CLS vectors to extract sentence embeddings. But in this paper, they try to use some templates like this sentence of X means mask, and the X is the sentence of your input, and you use the final layer representation of the mask token as your sentence embedding. So by doing so, you can actually get a much better result even you don't fine-tune the Bert model. And so to further boost the results, you can fine-tune this model with contrastive loss. And the way that they produce the positive pair is very special. They use two different templates to generate the sentence embedding from the same sentence. So these two sentence vectors can be used as a positive pair. And by doing so, their result is actually much better than SimCSE and also better than DivCSE. And it's almost the current state of the art. And after Bert, there is another paper further improve the performance of Bert by injecting ranking-based information. So in this paper, rank encoder, they try to refine the embedding space of existing models like SimCSE or Bert by injecting the ranking information from the whole corpus. So if you have a corpus with 5 sentences, you can compute the sentence embedding by SimCSE, so you have 5 data points here. And if you have a new input to the model, you can compute the cosine similarity between this input to all the other examples in the corpus. So you can obtain a ranking vector here. And if you have another input, you can also do the same thing to extract another ranking vector. However, you can observe that these two inputs are not very distant from each other, but their ranking vector are completely different. It's because you need to consider the interaction between the input sentence and all the other sentences in the corpus. So even though these two sentences are not very different, their ranking information may be very different. So this kind of ranking vectors actually increase the resolution of the embedding space if a specific region has a lot of data examples in the corpus. So it's kind of renormalizing the embedding space. And after we obtain this ranking vector, we can normalize the ranking vector and get a real sentence embedding to do the downstream task. And also we can further train a new encoder to match the cosine similarity of the ranking vectors to further boost the performance. Here the result of rank encoder is even better than Bert and all the other models we introduced previously. And this kind of framework can be compatible with all sentence encoders, so it's a very powerful technique. And here we can further investigate why rank encoder can achieve better performance by looking at the embedding space of this model. So you can see the embedding space of Bert. There are so many regions that has a lot of examples clustered together. However, because the rank encoder can be aware of the fine-grained interaction between the similar sentences, so it can smooth out these clusters. So the embedding space of rank encoder will be more uniform. And you can see the uniformity of rank encoder is much better than all the other models after applying this, injecting this ranking information. Okay, so that's all the content I want to show you today. And the conclusion I have here is that at the beginning, SimCSE told us the gap between unsupervised model and the supervised model is still very large. But after a lot of people continue working on this direction to improve SimCSE model, the performance of an unsupervised rank encoder now is comparable with a supervised SimCSE or a supervised from Bert. So it's very surprising that at the end, the gap between unsupervised model and supervised model can be reduced by a lot. And I expect that contrastive learning techniques can help us to better extract a representation from the existing pre-trained language models. That's all the content I want to share with you today, and thanks for listening, and I'm very happy to take any questions.